Okay. One thing I want to point out, and those of you who are in my other class, 610, this would apply to you too. Um, Now and then there's been some issues as students have brought to my attention with accessing my class website, and not the one in Canvas, but the one that's on the math department server, so math.usm.edu, um, where your browser will throw up some warning um, saying it's not a secure connection. And the reason for that is um, if a site is not its address is at HTTP colon um, slash, but not HTTPS, because it's a site that does not take any information from you. Um, it's only meant to disseminate. Um, so if you get this warning, like that, your browser should give you the option of like if you acknowledge the risks, then you can visit the site anyway. Um, then you can really get that way. And I tried to have I guess our unofficial department webmaster, which was Dr. Lee, to straighten it out. At the beginning of the semester, I thought he did, as it seemed that way, but I've had students telling me about this issue again. Um, so I guess this is a direct result of ITech negligence, which is a force that's very difficult to overcome. Um, so, um, so just so you know, yes, the site is safe to access, and now, of course, I have materials in Canvas too, but I know some people like to go to my personal web department, math department webpage, just because there's resources for all kinds of classes there, and so it's still valuable in that sense. But I mean, the notes and the videos and the assignments are in both places. Okay, so let's see what we got going today, and there should be some time at the end for any homework questions you might have. Okay. Okay. Today we're going to see a somewhat different type of problem that's going to require a very different approach. Um, so far we've been solving PDEs on a bounded interval, like x between 0 and L, or usually 0 to 1. But now we're going to look at PDEs defined on like the entire real number line, minus infinity to infinity, or a semi-infinite domain, like x going from 0 to infinity, in which case you would only have a boundary condition at x equals 0. Whereas if you have a problem that's from minus infinity to infinity, there are no boundary conditions at all, because at x, there is no boundary. And then in all these cases, you would still have an initial condition. So the approach that we're going to see for these kind of problems is called a integral transform, which loosely speaking does relate to what we've been seeing with separation of variables. In separation of variables, your solution is an infinite series, so it's a sum of a countably infinite number of terms. Well, now our problem's defined on an infinite or semi-infinite domain, so you're not going to have an infinite series. Instead, you'll have a uncountable combination of solutions, which ends up being an integral. Okay, so um, an integral transform, which can be referred to as an integral transformation, but integral transform is a term that's more often used, is an operation that takes a function to another function. So here we have a function of t, a little f of t, and then we multiply this by some function that's also of t, but also of another variable s that's a parameter. And this function is called a kernel. So because we're integrating with respect to t, and it's a definite integral, for each specific fixed value of s, we would get a number. But we also think of this as whole integral as a function of s. and we call that capital F of S. So we would say that capital F of S is this integral transform of little f of t. So it's mapping functions of one variable, like in physical space, to a function of another variable that's in could be called frequency space or some other kind of space, depending on the kind of integral transform you have. Now, how these are useful to us is they can be used to transform ordinary differential equation to an algebraic equation, or if you're starting for PDE, that depends on space and time, you can use the integral transform on like either your space variable or your time variable, and have, so your PDE gets reduced to an ODE, or it could be like a PDE in one variable less. So it's a way to make it very easy to deal with at least one of your variables. You may remember, depending on where you had like your first ordinary differential equations class, so Math 285 here, one of the topics we cover is a Laplace transform. So you have an ODE in time, and you take a Laplace transform, and that ODE gets changed to an algebraic equation. So that's an example of an integral transform that you may have already seen. Here we're going to see different integral transforms that have the same purpose, to drastically simplify whatever differential equation you're given. Because some of these transforms, it turns out to be very easy to express a transform of a derivative in terms of a transform of the original. So the Laplace transform has that property. Also the Fourier transform, which is what we're going to be working with here. Okay. Okay. So for instance, if we have a heat equation, ut is alpha squared uxx, we can do a transform applied to x. So that's going to get rid of all the partial derivatives with respect to x. All right. So then we can go ahead and if that reduces our PDE to an ODE, we can just solve the ODE. If there are no variables left, then what you have is the algebraic equation. What you could do is use different integral transforms in combination. Like I could use a Fourier transform to get rid of x, derivatives with respect to x. I can also use a Laplace transform to get rid of derivatives with respect to t, if I have no derivatives left, and only an algebraic equation to solve. Now, once you use a transform to simplify your PDE, you still have to go back to get a solution of your original problem. So what you have to do is you perform a transform, you solve a simpler equation, and then you use what's called an inverse transform to go back to the space that you started with. And that will give you the solution to your original initial boundary value problem. Okay. Now we do have a lot of transforms. And even if we say Fourier transform, which is our focus in this class, there are several Fourier transforms. Now, and how you choose one depends on certain things like what is the domain of your problem? What are the boundary conditions? So factors like that make it easier to choose which transform that you need. So if you have an initial condition, you take the integral transform of that too. If you know how to transform certain functions, you could undo those rules to figure out how to inverse transform functions. Just as in Calculus 2, you took all the rules that you learned for derivatives and you reversed them to get integration rules. So it's the same principle at work here. So I'm going to show you a table of certain transforms, and then I'll show you how they're used. Okay, so here we have the basic one, the Fourier transform of a function little f of x. So you're integrating from minus infinity to infinity. That times e to the minus I omega x. So notice it's complex. And this integral depends on the parameter omega. So your result is a function capital F of omega. So we say that big F is capital F is the Fourier transform of little f. So if you are solving a PDE on the entire real number line, then this is a good transform to use. Now, what I have here are 1, 2, 3, 4, 5 transforms: Fourier, Fourier sine, Fourier cosine, finite sine transform, finite cosine transform. And with each one, we have its inverse. And notice that the formula for a transform and its inverse are very similar. Like here, if I want to take capital F and inverse transform back to recover little f, notice the only change here, I have a sign. I have a minus sign here, but not here. It's still integrating from minus to infinity, infinity to infinity. We have a scaling factor of 1 over square root of 2 pi. Now, one thing I want to point out, notice all of these transforms have some kind of scaling factors in them. Different books use different scaling factors. I mean, all the transforms, no matter where you read them, are mathematically equivalent, but they may use different conventions as to what scaling factors they use. For example, I could take this 1 over square root of 2 pi and put it over here. So now I have 1 over 2 pi, and then I just have 1 here. So that's one notational convention to be aware of, that really there is no convention, but you have certain differences. Okay. Here we have a Fourier sine transform. So if you're solving a problem on the semi-infinite domain, x goes from 0 to infinity, but Dirichlet boundary conditions, that means that U has boundary conditions imposed on it at x equals 0, then this is a transform that you'll use. And notice here we have 2 over pi as a scaling factor. Here we do not. Here you have sine omega x, and you're multiplying by in both cases, just integrating from 0 to infinity in both cases. So again, a lot of similarity between each transform and its inverse. If you have Neumann boundary conditions, so du dx has a boundary condition imposed on it at x equals 0, then you use a cosine transform. And this is related to the fact that if you were doing separation of variables and you had Dirichlet boundary conditions, you'd have a sine series. Whereas if you had Neumann boundary conditions, it would be a cosine series. And then these two actually are literally from separation of variables. If this is your interval, 0 to L, so now bounded interval, which is why we use a finite sine transform, Dirichlet boundary conditions, then this is the actual sine series that you've seen already in examples involving separation of variables. And if it's Neumann boundary conditions on du dx, that's a cosine series. And this is how you get the coefficients. So these formulas we've actually seen already. You may remember, like if we're solving a PDE by separation of variables in the interval 0 to 1, so L is equal to 1, then what are your coefficients? 2 times the integral from 0 to 1 of your initial data times sine n pi x. So this is not really new territory here, but now I'm describing all the transforms in one place, just so you can see their similarities and differences. And we see here that when you're working on a bounded interval from 0 to L, your solution is an infinite series, so countably infinite number of terms. Whereas if your problem is on an infinite or semi-infinite domain, then instead of an infinite series for your solution, you have an integral, because it's almost like you're adding up an uncountably infinite number of terms. All right. So now what I want to do is, show how these are used to solve a PDE with whatever additional boundary conditions you have. All right, so suppose we have this kind of additional boundary value problem. So heat equation, semi-infinite domain, so x greater than 0, off to infinity. So here we have one boundary condition at x equals 0. So we say that u is equal to a constant value a at 0. And then we have, here's our initial condition that u of x 0, 0. So with the initial data being 0, you might think, oh, your solution is going to be 0. But we have a non-zero value here that's going to lead to a non-zero solution. So what you do is you have to select a transform. So you can go to this table. So first, we're looking at these two because these are on the domain x greater than 0. Now, what's the boundary condition? Well, a boundary condition is the condition imposed on u, not ux. Because it's u, that is a Dirichlet boundary condition. So this is the transform that we'll use, Fourier sine transform. Okay, so how does this work to actually carry out the transform? So what you do is you take the transform of both sides of the PDE. So what I'm doing right now is just the left side. So if I go to a formula for a Fourier sine transform right here, whatever I want to take a transform of, I multiply by sine omega x, and then take the integral from 0 to infinity, and I have to multiply by 2 over pi. So that's what I'm going to carry out on the left side. I'm taking a transform of du dt from right here. Now, the only thing in here that this entire expression that depends on t is u of xt. So I can take the partial derivative operator with respect to t, pull it out of the integral. Put another way, if I want to differentiate this whole thing with respect to t, because the only t dependence is right here, this ddt would only be applied to u. Okay. Now, the reason why I did this, why it's convenient, is because if I look at what's in the square brackets, that is exactly the Fourier sine transform of u. So what I end up with is partial derivative with respect to t of the Fourier sine transform of little u. So watch what happens here. Little u of xt, I take a Fourier sine transform, the t dependence remains. Partial derivative with respect to t remains. But x goes over to my Fourier variable omega. So a function of x and t becomes a function of omega and t. A differentiation with respect to any variable other than x just sticks around. Okay. So any questions about how this was transformed before I go to the right side? Okay. Oh yes, sorry, I forgot to comment this out. Yes, this fancy f of s of u, that is Fourier sine transform of u, whereas here we have Fourier sine transform of ut. So here we see a relationship between them. The transform of the derivative is the derivative of a transform. When it's not a derivative with respect to x, because we're transforming x, derivatives with respect to x are handled in an entirely different way. And that's what I'm going to show you now. How we handle the right side of a PDE, where we have alpha squared uxx. So now I'm transforming that. So that goes here. We're taking a Fourier sine transform of this function. Alpha squared is just a constant. Pull it out. Okay. So now I just have alpha squared, and I'm transforming uxx. Now, how do I do that? I'm actually going to use integration by parts. So if I want to evaluate this integral using integration by parts, remember your integration by parts formula is like integral of u dv. dv needs to be something that is easily integrated. Like, for example, if it's already a derivative. So if this is my dv, then my v is just ux. And then the rest of the integrand, that is the u from the integration by parts formula, so that is my sine omega x. So these are the boundary terms from my integrand. And then I have minus the integral of v and then du. I'm taking a derivative of sine omega x, which is where this factor of omega comes from. Okay. Now, here we have, okay. I need to evaluate this at x equals 0 and x equals infinity. If I plug in x equals infinity, this part's going to go to 0. So u is implied to have a valid Fourier transform in the first place, that this integral would only exist as long as u and its derivatives are going to 0 as x goes to infinity. So it can't be a function that's like growing with x. It has to be a function that decays to 0 at infinity. So I plug in x equal infinity, this whole thing will go away because of this part being 0. If I plug in x equals 0, well, sine of 0 is 0. So that goes away also. So in other words, these boundary terms go away completely. Now I need to handle this. The minus omega constant factor, I pull it out. Now I do integration by parts a second time. This is my dv. So v is going to be u of xt. So that's what I have here. This is my u, so that would go here. So then I have minus the integral of, this is my v, and then this is my du part. I take a derivative of cosine, which is minus sine, which is how this minus becomes a plus. And I have yet another factor of omega. Now, so now I have minus alpha squared times omega squared. Actually, I'm going to put an intermediate step in here to better explain what is happening here. All right, so now I have, all right, so I have the alpha squared on the outside. Okay. So I have minus omega squared. And then I have 2 over pi pulled in from outside. And then I have this integral from 0 to infinity of u times sine of omega x. Okay. And then I have this part here. So I have, okay. All right. If I let x go to infinity, again, this part will be 0 because u go to 0, x goes to infinity. But then I have minus the value at 0. Cosine of 0 is 1. So I can have minus u of xt. So now I move this minus 2 omega over pi inside. All right. And then from these boundary terms, I'm going to have minus u of 0t. But these become a plus, which is what I have down here. This right here, that's the Fourier sine transform of u. So that's what goes down here. So the transform of alpha squared uxx, we alpha squared just sticks around. And notice I have minus omega squared times the transform of u. So taking a second derivative with respect to x goes over with multiplying by minus omega squared. And then we have this additional term from the boundary. But u of 0t is equal to a by my boundary condition. So I fill that in here. And then the Fourier sine transform of little u is capital U of omega t. So now I'm finished with a transformation of the right side of a PDE. Any questions about what happened here? It's quite a bit. Okay. All right. So now if I put both sides together, okay, sorry, I have some LaTeX error here that's driving me nuts, but maybe I don't. Okay. Okay. So this comes from the left side, and here's what we have from the right side. So now my PDE, the heat equation, becomes an ODE. And the boundary condition has been taken into account right here. So I don't have to deal with a boundary condition anymore. What about my initial condition, though? An ODE is an initial value problem that needs an initial condition. By initial condition would be the Fourier sine transform of the initial data from your problem, the original problem. But that's 0 in this case, so we're just going to have 0. So now all we got to do is solve this ODE. So this is a linear ODE. So you make use of like an integrating factor, like you learned about in your introductory ODE course. So this is the kind of solution formula that we saw last time for non-homogeneous PDEs. It's the same integral formula being used here. So now we can evaluate this integral. All of this is just a constant. So we can pull that out. And so then once we evaluate this integral, we don't even need anything fancy here. And then we plug in the limits 0 and t, then this is what we get. So now we have not our solution. Our solution is little u of xt. We have the Fourier sine transform of our solution. So now we need to inverse transform this back to get the solution little u of xt. So how do we do that? We use a formula from a table. of transforms, inverse Fourier sine, that's this formula right here. So we can take our transform of our solution and plug it into this formula right here in place of capital F of omega, and we have to evaluate this integral. If we can. And what I mean by that is, in some cases, we may not actually be able to evaluate the integral, in which case we may have to write the solution as an integral, which is okay. So here's our formula for the inverse Fourier sine transform. Okay, so I plug this in. We have 2a over pi omega, constant, pull it out. So now we have this. Okay, and the reason why I write it this way is there are certain formulas, like there are tables of transforms, like the Fourier sine transform of this function is this function, and going backwards. So that's why I brought this 2 over pi back in, and also put the omega down here, because this is a known transform like you look up in a table. So the inverse transform of this function of omega is this function of x. Now, this is a rather strange function you likely have not seen before. ERF-C is the complementary error function. So ERF is just the error function, with a C means complementary. So the complementary error function is defined to be this. And the thing is, this is the simplest formula we can get, because it's well known, it's been proven that this kind of integral, an indefinite integral with a limit of x, there's no way to evaluate this. There's no way to express this antiderivative in terms of elementary functions. So we just leave it as an integral. And since the transform of this is not the complementary error function of x, but x over 2 times square root of a, and actually that whole thing belongs in the denominator. Want to be clear about that. Okay. So now, a little space in there. Okay. So now I can use this definition for the complementary function, where here I have a constant a that goes here. Here that constant is alpha squared t. So that's what goes in place of a in this formula. And I'll just fill in the parentheses I should have. Okay, so so that is the solution to our initial boundary value problem, expressed in terms of the complementary error function. So the idea is, from your initial boundary value problem, based on the boundary conditions and the domain, you choose your integral transform. You perform the transform on both sides of a PDE, which will give you an ODE in omega. Sorry, an ODE in t with parameter omega. You solve the ODE, which gives you the transform of your solution. Then you use a formula for the appropriate inverse integral transform, and that gives you your solution, little u of xt, of your original initial boundary value problem. Any questions about what transpired here? Now, a couple comments I want to make about this process. All right. In this case, we had a Dirichlet boundary condition. U of 0t was equal to a constant. If it had been a Neumann boundary condition, so du dx of 0t would be g of t for some given g of t, then we use it for a cosine transform instead of a sine transform. Now, to get the ODE from your PDE, depending on which transform you use, these are the rules that we use. If you have a Dirichlet boundary condition and you use a sine transform, like we just did, this is a rule that you use for handling second derivative with respect to x, so uxx. It's minus omega squared times the transform of your original function plus 2 omega over pi times the value of that original function at 0. So that's why you use this when you have a Dirichlet boundary condition, because then the right side of your boundary condition gets filled in here. If you have Neumann boundary condition, so it's on du dx at x equals 0 is equal to something, then you use a cosine transform. And notice the formula is very similar. It's just that here you have a minus, and then here you have the value of a derivative at x equals 0. So your value from your Neumann boundary condition is what will be filled in here. So these rules make it very easy to take whatever boundary condition you have into account. All right. Okay. And you take the transform of your initial data, whatever that may be, that gives you the initial condition for your ODE that you solve. And then you use the inverse transform to get the solution of your original problem. And if I show you this for a general problem where you have a Dirichlet condition at x equals 0, so the IBVP of this form. So heat equation, boundary condition imposed at x equals 0, and then some initial data. Then this is your solution, or expressed as an integral at least. And what you're taking the integral of comes from here. So this is your solution formula for the transform of your solution, where this capital phi of omega is the Fourier sine transform of your initial data. Whatever boundary condition you have here gets filled in here. So when you have a problem and you see that it's of this form, then you don't have to go through every little step that I did before. You can jump directly to this. And then, if possible, try to work out what this inverse transform is. But basically, you can take all of this and substitute it in here. So if you can inverse transform each of these terms individually and add them together, then you have your solution little u of xt. Now, how much you can do that depends on what these functions phi of omega and g of s are. Like, is it possible to evaluate these integrals? We've seen that's not always the case. And like for example, on a test, I would indicate that it's acceptable to leave a solution as an integral, or I might want you to evaluate the integral. Don't worry, I won't have you try to do something that's literally impossible. Okay. So that's a case where there's a Dirichlet boundary condition. U is equal to something. If this is a boundary condition, so du dx is equal to some given function of t, then what do you have for your solution instead? Well, what changes, the sine becomes a cosine, And then what you're taking the inverse transform of, we see that this part is the same. That takes into account the initial data from your original problem. And then this plus becomes a minus because of the rules for transforming UXX. And whatever boundary data you have goes in here. And that's all that changes. So if you have a problem on a semi-infinite domain with a Dirichlet ordinal Neumann boundary condition, then you can jump directly to the appropriate solution formula to have at least a transform of your solution, and then, if possible, try to work out the appropriate inverse transform from there. We will be seeing more of integral transforms like into the next lesson, but but there's a general idea that they used to give you a simpler problem to work out. You just have to transform a problem, solve a simpler equation like an ODE, and then transform back. Unfortunately, there's a lot of nasty integration exercises as part of working with integral transforms. All right. So, are there questions about what we've seen here or in any ongoing homework? Okay. Well, I see that 10 of you have turned in homework 2. That's 10 out of 16. So I look forward to grading those this weekend. So maybe it's like I say, anyone who might have asked questions is probably already done, and maybe the rest of you have not started yet. Actually, that'd be kind of a problem. So we don't want anyone falling too far behind. So really, no questions on homework at all.
I do have a homework question. I was waiting to see if somebody had a question on this stuff first before I asked the homework.
Okay, it's very considerate of you.
For homework 3, it's lesson 7, number 1.
Okay, let me navigate there real quick. Okay, I'm going to unshare and reshare. Dang it. Oh, okay. This one?
Yes.
Okay. Well, apparently I'd already been answering someone's question about that by these notes I've typed in here.
I got down to, well, I think I'm doing it correctly, but I got to the point where it's integration. And okay. In the notes, like one side is integration by parts. That's the like X sign. And that's fine. I think I can handle that part. But on the other side, you do 2 separate cases, like M doesn't equal N and M equals N. Do we do that every time?
Oh, okay. No, so what you have is okay, if I were to scroll through here. Okay, so in this case, with a boundary condition that you have, you're going to have So it's, instead of like sine n pi x, like if this had been u of 1 t equals 0, you're still going to have a sine function because of the left boundary condition. So what's going to happen is you'll whatever your solution xn of x is, like your sine function, you're going to okay, all right. So you yeah, you do need to know about the m equals n case because you have to divide by that. So okay, I'm gonna write a formula over here. Or actually, no, I'm gonna go back to the notes and write it there. Okay, 1 second. All right, so then I'll include this in what I post in Canvas later. Okay, so I'll put this on a new page. Okay. All right. So in all these separation of variables problems, regardless of the particulars, your solution being some combination, linear combination. Okay. And then by applying the additional condition, u of x0 is some function f of x that's given. And then what's happening in these heat equation problems is that if you plug in t equals 0, you get an exponential e to the 0, you just get 1. So you just have this. Okay. And then you're trying to find these coefficients an. So I want to give you the, and the thing is, what xn of x is depends on the particular problem. Like what's the domain? What's the boundary conditions? You know, sines or cosines. But regardless of any of that, because these functions that you get are orthogonal, you know, whatever domain you have, like interval 0 to L, that this integral is equal to 0 whenever m is not equal to n. This is your general formula for the coefficients an. And I mentioned this in, it actually came up in Monday's lesson, but that was about non-homogeneous PDE. But something similar applies for these, well, even if homogeneous. So your coefficient is, all right, so integral up top where you have your initial data times your x solution. And then down below is where you set m equal n, so you have xn of x squared dx. Now, for a case that that's come up in examples in class, where your intervals from 0 to 1 and xn of x turns out to be equal to sine n pi x, but it's because of a particular boundary conditions you have, the denominator turned out to be 1/2. That is why in those examples, in your formula for an, there was this factor of 2 out front because you were dividing by 1/2. So that's what would happen in this case, is that if you work out this integral, and generally what will happen when you're dealing with sines and cosines, that what you'll get for this will just be, even though it depends on n, it'll just turn out to be a number. So you'll have to work this out once, and that's your scaling factor for all of these. So I just don't want you to assume that the denominator is 1/2. It depends on what is your domain, what are these functions. But you can always use this. And I want to mention this comes from multiplying the equation I had earlier. If you multiply that on both sides by xm of x, this is called an inner product. So when you're multiplying two functions and integrating them, a definite integral in some domain, that's an inner product. So this is an inner product. Two vectors, which can be functions, that you're taking an inner product of, if the inner product turns out to be 0, then they are orthogonal. So that's what we're saying here, that they're orthogonal, meaning that their inner product is 0. This is analogous to what you learn about in calculus or linear algebra, vectors in Rn. You take their inner product, referred to there as a dot product, and if it's 0, then they are orthogonal, and they're geometrically very perpendicular in n-dimensional space. So that's the idea that you may be familiar with for ordinary vectors applies just as well to functions. You just need the appropriate definition of an inner product. And that's why having functions that are orthogonal in a sense is quite nice, because it makes it easy to compute these coefficients. We want to express f in terms of these functions. We need an easy way to get the coefficients, and that's what we have here, because we can compute these independently of one another. And that's what orthogonality gives us.
So are they always, like, we can assume they're orthogonal?
Yeah, and the reason for that is all of the problems that we are examining in this class are what I mentioned a couple class periods ago, Sturm-Liouville problems. So those are a PDE in X of a certain form, where it's proven that solutions of that kind of problem that satisfy the boundary conditions are known to be orthogonal. So so yes, for these kind of problems, you could take that for granted.
Okay, thank you.
Are there any other? Okay. Since no one's asking questions, I'm going to expound on what I was just talking about. So when we're solving PDEs, separation of variables, and you separated the two ODEs, one for t, one for x. The ODE for x, so that's what I'm referring to is a Sturm-Liouville problem, and that's from the prior notes, but I'm going to give it here. So it's an ODE of this form. In most cases, Q is 0 and P is a constant, which allows us to get solution formulas for these, but it's anything that fits this form. And as I mentioned in earlier notes, that solutions that correspond solutions that satisfy the boundary conditions, whatever boundary conditions you are given. So that's a very important point. That are Eigen Functions. Okay, of the differential operator L, because a differential operator is an operator that takes as input a function, computes derivatives, multiplies by coefficients, and produces another function. So we have all these infinitely many solutions, x1, x2, and so forth. And each one of these is a solution with values of lambda that work. And I say by working, I mean in terms of the boundary conditions. Okay. Remember, boundary conditions determine everything here. Okay. Now, suppose we have two solutions to this problem. I'll call them x1. Whoops. Okay. So is a solution, x1 is a solution. So L of x1 is lambda 1 x1. And another solution x2 for a different eigenvalue lambda 2. So I'm going to make it explicit that these lambda values are different. Okay. Then, if I look at this integral on whatever domain I have, 0 to L, of x1 times L applied to x2. Okay. Well, L of x2 is lambda 2 x2. Constant lambda 2, I'd pull out. But we also have the following. And this actually is something I wrote up in the notes from last class. I had to do it after class, and it's posted, so you can see it in Canvas. I won't go through all the details here, but this same integral, using integration by parts twice, using the fact that both of these functions, the xi's, satisfy the boundary conditions, so both facts are essential. This integral happens to be the same as if I put the shoe on the other foot. If I had x2, I'll apply to x1. Well, following what I did here, that's the same as lambda 1 times the integral of x1, x2. Notice I started with the same thing on the left side. So these must be equal. So I can move them all to one side. Set equal to 0. All right, so that's all I did here. Well, this is non-zero because I've stipulated that lambda 1, lambda 2 are not equal. Therefore, this must be 0. Okay. So since I brought up earlier that yes, for these problems, yes, you take it for granted that whatever solutions you get from your separation of variables, your xn of x, that they will be orthogonal. So I thought since nobody had any questions, I thought I would take a few minutes to prove that for you. This goes along with something from just ordinary linear algebra, like involving matrices. That if you have a matrix and you have eigenvectors corresponding to distinct eigenvalues, when it's a symmetric matrix, they must be orthogonal. Okay. And in general, they must be, even if matrix not symmetric, they must be linearly independent. Okay. So this is what you get for not asking questions when there's still time left. So, not that I mean this as punishment, and hopefully you don't take it that way, but since I was just talking about that, I figured I'd just take a few moments to prove it. Yeah. Okay. So that may have given you a little time to consider if you have any questions. So once again, last chance. I have no more things to throw at you today. Are there any questions, especially on homework? Okay, I guess we will all agree that we have, or especially you all, have suffered enough. So I will end the recording here.